Welcome back again. Today, inshallah, we're gonna see a simple experiment by using FET, which is a virtual lab. Simply now, the light will travel from a medium with lower index to a medium with higher index. On the upper part we have air, and on the lower part we have glass. Since the light is traveling from a medium with lower index to higher one, so the light will refract toward the normal. Simply, as we see here, the light is going downward a little bit, is moving downward a little bit toward the normal. Simply, once also we change, increase or decrease the angle of incidence, always it still deviates downward toward the normal. And here we have the angles. So far so good. Now if we change the medium, if we take for example water and let's say air. So let's take water and air. Simply, the light now will travel from a medium with higher index to a medium of lower index of refraction. Once here we have from higher index to lower index, the ray will refract away from the normal and toward the surface, as we see here, by increasing or decreasing. If we increase, for example, always, as we can realize here, the refracted ray will still a little bit upward away to the normal, tries to go away from the normal, of course the refracted ray, by increasing or decreasing the angle of incidence. So far so good. Last time also we talked about the critical angle. We said that critical angle simply it's a limit. It's a limit. Once angle of incidence exceeds this limit, so it will go a total internal reflection, as we see here. Here the angle of incidence is much more and it's greater than the angle, the critical angle. Critical angle, of course, it's not given here, but now as we see here, of course, at 49.5 or 48.7, it exceeded the critical angle. Here the critical angle, it's about 47, or it's about 48 point something, 48.5 or 0.6. Also, as we see here, the maximum angle can be reached here for the angle of refraction is 86.4. We cannot catch it at all at 90 degrees exactly, as we saw in the second case when theta I is equal to the critical angle, or when theta 1 here the angle of incidence is equal to the critical angle. So far so good. So once the angle of incidence is less than the angle, the critical angle, simply the refraction will be away from the normal and toward the surface. Now when the critical angle is equal exactly to the angle of incidence, here we'll do our best to reach it. No, the maximum that could be reached is 86.3. No problem, it's okay. So once theta 1 equals to theta c, once the angle of incidence equal to the critical angle, simply the refracted ray grazes on the surface. Once theta 1, if you kept increasing theta 1 until it reaches or until it exceeds this limit, which is the critical angle, simply a total internal reflection will occur, and in this case there is no refraction at all. So far so good. As we see here we have the wavelength. The wavelength for each light. For example, red light, it has the wavelength 650 nanometers. Once we change the wavelength, simply we are changing the color, and at the same time frequency will change, as we see here. So far so good. And we can use waves also instead of ray light, since it's electromagnetic wave, of course. So far so good. Now here we have actually two mediums, air, glass, then air. First of all, I will draw the normal on the surface of each medium. Here you have the normal, which is perpendicular. Also here is perpendicular. Here another normal, and here another one. So far so good. Now, in the first case, n equals to 1, here n equals 1.5, sorry, and here n equals 1.1 exactly, and it's unitless. Now, so from lower index to higher index, then to lower index. First of all, since the light is traveling from, let's take for example this one, since light is traveling from a higher index, which is this one, from lower index to higher index, which is n equal 1.5, the light will deviate away from the normal. The light will deviate, toward the normal, as it's shown here. Here the angle of refraction, which is theta 2, small theta 2, decreased. And here you have the angle of incidence, which is theta 1. Now, in the second case, when the light travels, let's take this ray right now, when light travels from a medium of higher index to a medium of lower index of refraction, so in this case, the light will deviate away from the normal as shown here. Here we have approximately the normal, and here we have the refracted ray, which is away from the normal, since it's moving from a medium with higher index to a medium of lower index of refraction. Always, guys, once you have a medium with higher index of refraction, it means the speed of light will be less. As we see here in air, it's approximately 3 times 10 power 8 with lower index of refraction, while it's 2 times 10 to the power 8 meters per second at n equal 1.5, يعني at a higher index of refraction. So far so good. Now, Snell's law. Snell, as a scientist, he found a relation between angle of incidence, angle of refraction, index of refraction of the second medium, index of refraction of the first medium, speed of light of the first medium, speed of light of the second medium, wavelength of the first medium, wavelength of the second medium. So sine theta 1 divided by sine theta 2 equals n2 over n1 equals v1 over v2 equals lambda 1 over lambda 2. All of these starts with 1, let's say sine theta 1, v1, lambda 1 in the numerators, except n, except the index of refraction n, and it starts with n2. Down, sine theta 2, n1, v2, lambda 2. So all of them 2 except n1. That's why n2, n1, or the index of refraction, is inversely proportional here to the speed, inversely proportional to the wavelength, and etc. So far so good. So in order now to find, let's say for example, theta 1, maybe n1, n2, theta 2 will be given, so we're gonna use the one on the left side, the left part. If let's say v1, v2, lambda 1 given, and we need to find lambda 2, we're gonna use the right side. Everything depends on the given. Everything here depends on the given, so be careful about the given. So maybe you're gonna use the first part, maybe you're gonna use sine theta 1 over sine theta 2 equals lambda 1 over lambda 2, and as we said, everything depends on the given, so you should be careful about it. Now, dispersion of light by prism. It's a very important concept. First of all, as we see here we have a light ray, white light ray. Once this light ray, which is white color, enters a prism, it splits into 7 main colors. And these 7 main colors are the rainbow colors: rouge, bev, red, orange, yellow, green, blue, indigo, and violet. In this figure here, I will take only the red one and the violet one. The red light has high wavelength and low frequency. While the violet color has a high frequency and low wavelength. So the red one, it has the minimum frequency within these 7 colors, minimum frequency and the maximum wavelength, while the violet color, it has the maximum frequency and the minimum wavelength, of course, within these 7 colors, and they are the spectrum colors, the colors simply that you can see. So dispersion of light, simply it's the separation or the spreading of the white light, which is the main light that contains these 7 colors. So it's gonna spread into a red color, orange color, and here you have the yellow one, the green, the blue, indigo, and finally the violet color. So this is the main concept behind the dispersion of light. Also, we can see it here on the FET simulation. Here you have prisms. Okay, we're gonna take this one. Here we have the red color. Look what will happen to the red color. So in this case, it's gonna refract inside the prism. And here, so when red color enters from, for example, air to glass, simply it's gonna refract. And then from glass to air, also it's gonna refract more and more. Here I can change the colors also, as we see here. Simply each color gonna refract by a different angle, The minimum, as we said, the minimum wavelength, it's the maximum wavelength and minimum frequency is the red light, and the violet one, it has the minimum wavelength and the maximum frequency. Now it will be clear. Now here we have the white light, and as we can see here, we have the rainbow colors. So red, orange, and the other colors till we reach the violet one. Let me change the prism. Let's use this one. This one shows not all of the colors, of course, maybe 3 colors. And these colors are the blue one, and the orange one, and the dark green one. And here by changing the angles, everything, guys, depends on the angles. On this angle, these lights gonna be shown, these colors. And on this angle, let's see here. These colors, and here we have these colors. So everything depends on the chosen also angles for each color. So far so good. Now here we have a certain summary for the 3 cases when the light travels from a higher index to lower index. First of all, when light passes perpendicular to the surface, it will continue without any deviation. Let's say here we have, for example, a certain coin, and you want to see this coin from outside. Now, since here it's perpendicular, so it will continue, the light will continue in a straight line without any deviation. Here we have, in this case, an angle which is theta 1. This theta 1 is less than the critical angle. Once the light ray deviates away from the normal and toward the surface, once it deviates away from the normal, here we have theta 2, which is the angle of refraction, and toward the normal, toward the surface, so theta 1, it will be less than theta c. This is the first case. The second case, when now the coming light ray, which is here, as we see here, theta c. Theta c in this case, it's the same as what? Theta 1. So theta 1 and theta c here are the same. Why? Since the light ray grazes on the surface. Since the refracted ray grazes on the surface and it makes angle 90 degrees with the normal, so theta 2 here is 90 degrees, so theta c, it will be exactly equal to theta 1, and it's the only case where theta c shown on the figure. It's the only case where the theta c shown on the figure, only this case when theta 1 equals to theta c. And finally, we have here theta I, and here we will have theta r from lesson 17.1. Once theta 1 exceeds theta c, once theta 1 exceeds the limit, so theta 1 greater than theta c, a total internal reflection will occur. Simply I, it will be equals to r. So far so good. This I, of course, it means the angle of incidence. We can put it I equals to r, or we can put theta I equals theta small r from lesson 17.1. Now, we're gonna start solving examples. First of all, example 1. Light travels from air, which is n equals to 1, lower index of refraction of course, into glass, where its velocity reduces to only 2 times 10 to the power 8 meters per second. So the speed of light in glass is given as 2 times 10 to the power 8, and the index of refraction is given for air, of course, by 1. What? For air. What is the index of refraction in glass? So we need to find the index, which is n in glass. Here we can use n equals simply c divided by v. N equals c over v, where c is the speed of light in vacuum or in air. Since they are close to each other, 3 times 10 to the power 8 divided by v, which is 2 times 10 to the power 8. So in this case, 10 power 8, 10 power 8 cancels out, so it will be 3 over 2, which is 1.5. N equals 1.5. And it's the index of refraction that's related to glass. So implies that n equal 1.5. And it's unitless. Since the speed of light, the unit of the speed of light is meters per second in vacuum or in air, and the speed of light in glass also meters per second. So cancels out. Example number 2. Now, it's a very important example. A laser beam is in a darkened room, strikes the surface of water at an angle of 30 degrees. So here there's changing also in medium from less index to higher index. Of course it will be given. So on, in this case n equals 1 in air and n equals 1.33 in water. So far so good. The angle here makes 30 degrees with the surface of the water. So the velocity in water is 2.26 times 10 to the power 8 meters per second. What is the angle of refraction? So we need to find theta 2. We need to find theta 2. First of all, actually theta 1 is not given. Or it's given but in an indirect way. How? Normal here is 90 degrees with the surface. And here we have also angle 30 degrees. So we need to find theta 1. First of all, theta 1 equals 90, which is the total angle, minus 30 degrees, which is this part of this total angle. It will be 60 degrees. So theta 1 is 60 degrees. This is theta 1, 60 degrees. So the angle between the incident ray and the normal, which is the angle of incidence, is 60 degrees, and we need to find, in this case, theta 2. Simply, now by using Snell's law. So sine theta 1 divided by sine theta 2 equals 2. N2 divided by N1 equals to V1 divided by V2 equals to lambda 1 divided by lambda 2. N1 is given, N2 is given. Here we have N1, here we have N2. Theta 1, we already found it, and we need to find theta 2. Everything is given here. Simply, we're going to use the first part of the equation. Since in the given, we have the indices of refraction and theta 1, theta 2. And we need to find theta 2. So sine theta 1, which is 60 degrees, sine 60, divided by sine theta 2 equals N2 over N1. N2, which is 1.33, divided by 1, which is the index of refraction in air. Implies that now sine theta 2 is equal to 0.65. Don't forget to do the shift sign. Implies that theta 2 equals 40.5 and approximately 41 degrees. So theta 2 is approximately 41 degrees. Always, once the light is traveling from lower index to higher index, theta 1 will be greater than theta 2. Theta 1 is 60, theta 2 is 41 degrees. Now example number 3. A helium neon laser emits a beam of wavelength 632 nanometer in air. N1 equals to 1. So in air, the index of refraction in air. What is the wavelength inside a slab of glass N2? So N1 is given, N2 also is given, and we have the wavelength lambda 1 in air. Of course, it will be lambda 1. So lambda 1 equals 632 nanometers, N1 equals 1, N2 equals 1.5, and we need to find lambda 2. According to Snell's law, we have N2 over N1 equals lambda 1 divided by lambda 2. Now we need to find lambda 2. Simply implies that lambda 2 equals, in this case, N1 lambda 1 divided by N2. Simply substitute 1 times 632 divided by N2, which is 1.5. So it's 421.3 nanometers. So also from lower index to higher index, lambda 2 is less than lambda 1. Only once you travel from, for example, from lower to higher, as we see here, only N2 will be more than N1, while the speeds will be less, and the wavelength also will be less. Example 4. Find the critical angle of incidence from water to air. So here we have from water to air, theta c. According to the figure here we have the refracted ray grazes on the surface. Since it grazes on the surface, so we can deduce that theta 1 it's the same as theta, so theta c is the same as theta 1. So if we find theta 1, actually we are finding, in this case, theta c. So now how we can find theta 1? Simply also by applying Snell's law. Sine theta 1 divided by sine theta 2 equals N2 divided by N1. Implies that sine theta 1, we need to find theta 1 since it's unknown. We have the N2 given, N1 given, and theta 2 is also given. Sine theta 2 يعني actually we are talking about sine 90. So theta 2 is 90 degrees here in this case. Equals n2 is 1.33 and 1 also 1. Implies that sine theta 1 equals sine 90, which is 1 times 1.33 divided by 1. So equals 1.33. Now, don't forget in this case to find here, sorry, there's a simple mistake, and 2 here, it will be 1. I converted these two. I reverted them, no problem. So N2 here is 1 and N1 is 1.33. Be careful for this step. N1 here is for water and N2 is air, since light is traveling from water to air, so from N1 to N2. So up is 1 and down is 1.33. Also here and up we have times 1. So sine 90 divided by 1.33, we will get 0.75. Shift sine 0.75, so we will get 48.5, which is approximately 49. Implies that theta 1, which is the same as the critical angle theta C, it's approximately 49 degrees. So it's 48.5 or approximately 49 degrees for simplicity. So now we can deduce that if theta 1 is less than theta C, let's say if theta 1 is 40 degrees, so the light ray will deviate away from the normal and toward the surface. If theta 1 equals to theta C, like in this case, so it grazes on the surface as we see here. And if theta 1 exceeded theta C, if it's more than theta C, let's say 50, so the light will go a total internal reflection. So far so good. So this is the last slide in our lesson, and see you on other videos inshallah, and good luck.